class in linear algebra. Today we will take up the properties of matrix multiplication, transpose of a matrix, adjoint of a matrix, and the properties of transpose matrix and adjoint of matrix. We start with the properties of matrix multiplication. We let A, B, C be three matrices. In the following properties, we assume that the products that appear in these properties are defined. And we already know the conditions for the product of two matrices to be defined. The number of columns of the first matrix in the product should be equal to the number of rows of the second matrix in the product. And the first property says that A times quantity BC, or A times the product of the matrices BC, is equal to quantity AB times C, or the product of AB multiplied by matrix C. And this property of matrix multiplication is the associativity property. That is, multiplication of matrices satisfies the associative property for matrix multiplication. The second property is a scalar multiplied by the product of matrices A and B. So A, the scalar A multiplied by the product of matrices A and B is the same as the product of the scalar product of A and matrix A and matrix B. In the third property, we have the product of the identity matrix I. And we already know that the identity matrix denoted by capital I is a diagonal matrix whose entries in the diagonal are 1 and the rest of the entries of the identity matrix are 0. Moreover, the identity matrix is a square matrix. And if you multiply an identity matrix by any matrix A, the product is the matrix A. And number 4, we have the product of matrix A and the zero matrix. And we said before that the zero matrix is a matrix all of whose entries are 0. And if a matrix A is multiplied by the zero matrix, the product is 0 matrix. Similarly, the product of 0 times any matrix B is equal to the zero matrix. Now, the P property is very much similar to the definition of a real number a, small a to the power n. By definition, the expression a to the power n is small a to the power n is equal to the product of a with itself, or a, the small real number a, is multiplied by itself n times. In the same way, the expression a to the power n, the matrix A is raised to the power n, is equal to the product of matrix A with itself n times. That means A is multiplied by itself n times. So A to the n is, in its expansion, we have n factors of A. And you will notice that in these properties of matrix multiplication, commutativity is not one of the properties. That is, matrix multiplication does not satisfy the commutative property under matrix multiplication. That is, if you multiply the matrices A and B, the product AB may not be equal to the product BA. Although both products AB and BA may be defined, they may not be equal in general. And we already said that two matrices to be equal have to have the same size, and the corresponding entries should be equal. We now define the transpose of a matrix A. Define the transpose of a matrix, and this definition gives us a way of how to find the transpose of a matrix. We let A be element of M sub M cross N of R. This is the set of all matrices of sizes M by N, and the entries of the matrices elements of M, capital M, are real numbers. So if A is element of M sub M by N of R, then A is a matrix of size M by N, and the entries of matrix A are real numbers. Then the transpose of A, denoted by A to the power capital letter T, or A transpose, you read as A transpose, is the transpose of matrix A, is an N by M matrix. Originally, the size of matrix A is M by N, and the size of its transpose is N by M. Thus, if you have a given matrix and you get its transpose, the number of rows of the transpose of the matrix is the number of columns of the given matrix, and the number of columns of the transpose of the matrix is the number of rows of the given matrix. And the ij entry of the transpose of matrix A, the ij entry in A transpose is the ji entry of the matrix A. If we let capital B be A transpose or the transpose of A, then we write the entries of matrix B as B sub ij. This is B sub ij is the entry in the ith row and jth column of matrix B, which is the transpose of matrix A. And this ij entry, this entry in the ith row and jth column of A transpose is equal to the entry in the jth row and ith column of matrix A. This means that to get the transpose of matrix A, you simply write each row as column of the transpose of the matrix. You write each row in order as columns of the transpose of the given matrix. We now take an example. For our examples in getting the transpose of a matrix, consider the following matrices. Matrix B has entries in the first row 3, negative 1, 2, and entries in the second row of matrix B are 0, 5, 1. So you can say that B is a 2 by 3 matrix. It has 2 rows and 3 columns. And when we get the transpose of matrix B, we can tell in advance the size of the transpose of matrix B. And the size of the transpose of matrix B should be 3 by 2 with 3 rows and 2 columns. C is a square matrix and it has 3 rows and 3 columns. Hence, by definition, the size of the transpose of matrix C, denoted by C to the power T, is also 3 by 3. Now we get the transpose of matrix B, denoted by B to the power T. As I said earlier, to get the transpose of a matrix, you write each row of the given matrix as columns. So the first row of matrix B, 3, negative 1, 2, we write these entries as the entries in the first column of the transpose of matrix B. And the entries in the second row of matrix B, we write as entries in the second column of B transpose. And this is the transpose of matrix B, and the size is 3 rows and 2 columns, 3 by 2. Now we get the transpose of matrix C. The transpose of matrix C is obtained by writing the rows of matrix C as columns of C transpose. The first row of matrix C, 2, 3, 5, we write as the entries in the first column of C transpose. 2, 3, 5. And the entries in the second row of matrix C, 3, negative 1, negative 2, we write as the entries in the second column of C transpose. And the last entries in the last row, 5, negative 2 of matrix C, we write as the entries in the last column of C transpose. 5, negative 2, 0. entries of C transpose 2, 3, 5, 2, 3, 5, 3, negative 1, negative 2, 3, negative 1, negative 2, 5, negative 2, 0, 5, negative 2, 0 are exactly the entries of the given matrix C. So the transpose of C is equal to C. Now, by inspection of the given matrix C, you can say that matrix C is a symmetric matrix. A symmetric matrix has the property that the entry is the ith row and jth column of matrix C is equal to the entry in the jth row and ith column of matrix C. That is, with respect to the diagonal of the matrix C, the matrix is symmetric. This is the entry in the first row and second column, and it's equal to the entry in the second row and first column. This 5 is the entry in the first row and third column, and it is equal to the entry in the third row and first column. And also negative 2, the entry in the second row and third column, is equal to the entry in the third row and second column. This entry negative 2 is the entry in the second row, third column, and it is equal to this entry negative 2 in the third row and second column. Thus, matrix C is a symmetric matrix, and this is actually one of the properties of matrix transpose. If a matrix is symmetric, like matrix C, the transpose of a symmetric matrix is equal to itself, the given matrix C. We now write the properties of matrix transpose, also known as the laws of transposition. We let A and B be any two matrices, and of course for the sum and difference of the matrices A and B should have the same size or shape. And in these properties, we assume that the sum or difference and product of matrices A and B are defined. The transpose of a sum or difference of two matrices A and B is equal to the sum or difference of the transposes of matrices A and B. That's the first property of matrix transpose. The second property is the transpose of the scalar product of the scalar A and matrix A. The transpose of small a multiplied by matrix A, scalar A by matrix A, is equal to the scalar A multiplied by the transpose of matrix A. And number three, the third property, the transpose of the product of matrices A and B is equal to the product of the transpose of B and the transpose of A. And number four, which we have shown in our second example for matrix C, if matrix A is symmetric, then the transpose of a symmetric matrix A is equal to the matrix A. We now prove the first property of matrix transpose. We now prove that the transpose of a sum of two matrices is equal to the sum of the transposes of the two matrices. In particular, we now prove that the transpose of the sum of matrices A and B, A plus B, is equal to the sum of the transpose of A and the transpose of B. In this sum A plus B, we assume that A and B have the same size or shape so that the sum A plus B is defined. We let A be a matrix whose entries are denoted by A sub ij. A sub ij is the entry in the ith row and j column of matrix A, and the values of I goes from 1 up to the number of rows of matrix A. And j, the values of j goes from 1 up to the number of columns of matrix A. And the number of rows and number of columns of matrix B are the same as the number of rows and number of columns of matrix A for the sum, so that their sum A plus B is defined. Thus, the value of I goes from 1 up to the number of rows of matrix A, which is equal to the number of rows of matrix B. And J goes from 1 up to the number of columns of matrix A, which is equal to the number of columns of matrix B. And B sub ij denotes the entry in the ith row and j column of matrix B. Now we get the sum A plus B. By definition of addition of matrices, we add the corresponding entries. Thus, the ij entry of matrix A, we add to the ij entry of matrix B. And A sub ij plus B sub ij is the entry in the ith row and j column of the sum A plus B. And we denote the sum A plus B by matrix capital C. Thus, the entries of A plus B, if we denote it by capital C, are denoted by small c sub ij. C sub ij is the ith entry, the entry in the ith row and j column of A plus B. And this C sub ij entry of A plus B is equal to the sum of the ij entry of matrix A and the ij entry of matrix B. Now we get the transpose of A plus B. If we denote the transpose of A plus B, or if we denote A plus B transpose by capital letter P or as matrix P, we denote the entries of A plus B transpose by small p sub ij. And by definition of transpose matrix, this ij, the entry in the ij, in the ith row and j column of A plus B transpose is equal to the entry in the j row and I column of the sum A plus B. But by definition, if C sub ji is the entry in the j row and I column of A plus B, then C sub ji must be the sum of the corresponding entries in the j column and in the j row and I column of matrix A, and the entry in the j row and I column of matrix B. Thus, C sub ji is equal to the matrix whose entries are actually the sum of the entries A sub ji plus B sub ji of matrices A and B. C sub ji is the entry in the j row and I column of A plus B. And because it is the entry in the j row and I column of A plus B, then it must be a sum of the corresponding entries in the j row and I column of matrix A and the entry in the j row and I column of matrix B. But by addition of matrices, we can separate this as the sum of the matrix with entries A sub ji plus the matrix with entries B sub ji. On the other hand, A transpose, we write, but A transpose, if we denote it by matrix M, capital M, then its entries are denoted by M sub ij. And by definition of matrix transpose, the entry in the ij entry in A transpose is equal to the entry in the j row and I column of matrix A. Similarly, the transpose of matrix B we denote by capital N, and if we denote capital N as the transpose of matrix B, then the entries of capital N or B transpose are denoted by N sub ij. But by definition of matrix transpose, the entry in the ij entry in B transpose is equal to the entry in the j row and I column of matrix B. Therefore, we go back to this statement. A plus B transpose is equal to the matrix with entries A sub ji, but this matrix with entries A sub ji is equal to A transpose, the matrix A transpose, plus the matrix with entries B sub ji, and we have shown that this matrix with entries B sub ji is the transpose of matrix B. Therefore, we conclude that the transpose of A plus B is equal to transpose of A plus transpose of B. And we indicate the end of proof by this small shaded rectangle. We now state the last property of matrix transpose. The last property of matrix transpose says that the transpose of A is equal to A. If you get the transpose of a matrix twice, then the result will be equal to the matrix given. Very similar to the property of complement of set. The complement of a set is equal to the set. We now define adjoint of a matrix. We now define the adjoint of a matrix. We let matrix A be any matrix elements of the set of matrices with sizes m by n and whose entries are real numbers. So if A is element of set M sub m by n of R, then matrix A is an m by n matrix with m rows and n columns, and the entries of matrix A are real numbers. Then the adjoint of A, written A to the power star or A star. A star denotes the adjoint of matrix A, is an n by m matrix. The original matrix A has a size of m by n. So the definition says the size or shape of the adjoint of matrix A is n by m. That is the number of rows of the adjoint of a matrix is equal to the number of columns of the matrix. And the number of columns of the adjoint of a matrix is equal to the number of rows of the matrix. And the ij entry of A star, the adjoint of matrix A, is the complex conjugate of the ji entry of the transpose of A. That is, if A is a matrix with entries A sub ij, and the adjoint of matrix A, denoted by A star, have entries B sub ij, then the ij entry of the adjoint of A, or A star, is equal to the conjugate, denoted by this bar on top of A, complex conjugate of the ji entry, A sub ji entry. A sub ji entry is actually the entry in the j row and I column of A transpose, and you take its complex conjugate, that will be the entry in the ith row and j column of adjoint of A. This definition tells us that it will take two steps to get the adjoint of a matrix. First, you get the transpose of the matrix, then you take the complex conjugates of the entries of the transpose of the matrix, and the resulting matrix is the adjoint of the matrix. We now take one example. Consider matrix A with entries 3, -1, 2, and 5, 2, 0. Thus, A is a 2 by 3 matrix with 2 rows and 3 columns. And even before you get the adjoint of matrix A, you can already predict the size or shape of the adjoint of matrix A. And the size or shape of the adjoint of matrix A, denoted by A star, should be 3 by 2 with 3 rows and 2 columns. And the first step is to get the transpose of the given matrix A. As we said earlier, to get the transpose of a matrix, you write the rows of the given matrix as columns of the transpose of the matrix. Thus, to get the transpose of A, denoted by A transpose, we write the first row of matrix A as the entries in the first column of A transpose. And we write the entries in the second row of matrix A as the entries in the second column of A transpose. And from the transpose of matrix A, or A transpose, we get the conjugate of matrix A, denoted by A star. And we get the entries of the conjugate of matrix A, denoted by A star, by getting the complex conjugate of the entries of A transpose. And how do we get the complex conjugate? Complex conjugate applies only for complex numbers. And to get the conjugate of a complex number is simply to take the opposite side of the imaginary part of the complex number. We take an example. Consider the complex number z equals negative 5 plus 3i. Negative 5 is the real part of the complex number c, and plus 3i or positive 3i is the imaginary part of the complex number c. The conjugate of c is denoted by z bar. And the conjugate of the complex number c is obtained by simply taking the opposite sign of the imaginary part. We do not do anything with the sign of the real part. Regardless of whether it's positive or negative, the sign of the real part will be the same in the conjugate of the complex number. So negative 5 will remain as is in the conjugate of the complex number c, denoted by z bar. But we take now the opposite sign of the imaginary part 3i. The opposite sign of plus is minus. Therefore, in the conjugate of complex number c, denoted by z bar, you will get minus 5 minus 3i. And that's how you get the complex conjugate of a complex number. Simply take the opposite sign of the imaginary part of the complex number. What happens? We said that every real number is a complex number. We take an example. How do we get the conjugate, the complex conjugate of a real number? Here is a real number, but it is a complex number because it can be written in the form 3 plus or minus 0i, where the real part is 3 and the imaginary part is either plus 0i or minus 0i. But when you simplify 3 plus or minus 0i, it simplifies to 3, which is a real number. Thus, the real number is a complex number. And if you take the conjugate of this real number 3, denoted by z bar, we take the opposite sign of the imaginary part. The opposite sign of plus is minus. The opposite sign of minus is plus, and we do nothing with the real part of the complex number. So 3 will remain 3 as is in the conjugate of c, denoted by z bar. And the imaginary part, after taking the opposite sign, will become minus plus 0i. But if you simplify 3 minus plus 0i, it simplifies to 3, which is the given complex number c. Thus, if the complex number is a real number, its conjugate is equal to itself. That is, the complex conjugate of a real number is equal to the real number. So we apply those properties, those definition of complex conjugate to get the complex conjugates of these entries of A transpose. But you can see all the entries of A transpose are real numbers, so their complex conjugates are equal to themselves. That is, the complex conjugate of 3 is 3, the complex conjugate of 5 is 5, and so on. Therefore, the adjoint of A, denoted by A star, is the same as the transpose of A. Now suppose we get again the adjoint of A star, the adjoint of A. And the first step is to get the transpose of A star. The transpose of A star or the transpose of adjoint of A is obtained by writing the rows of A star as columns of the transpose of A star. So the first row of A star 3, 5 we write as the first column of the transpose of A star. 3, 5. And the second row of A star we write as the second column of the transpose of A star. Negative 1, 2 will be the second column of the transpose of A star. And the last and third row of A star is written as the third column of the transpose of A star. And we get now the complex conjugates of these entries of the transpose of A star. And the result is the adjoint of A star, denoted by A star star. This is the adjoint of matrix A, whose entries are the complex conjugates of the transpose of the adjoint of A. But all the entries of the transpose of the adjoint of A are real numbers. Therefore, the complex conjugate of each is equal to itself. The complex conjugate of 3 is 3. Complex conjugate of negative 1 is negative 1, and so on. But by inspection of the conjugate of A, 3, negative 1, 2, 5, 2, 0, this is exactly the even matrix A. 3, negative 1, 2, 5, 2, 0. Thus, we have shown that the conjugate of a matrix is equal to the matrix. Very similar to the property of matrix transpose. The transpose of a matrix is equal to the matrix. And this is actually one of the properties of adjoint of matrix. We now write the properties of matrix adjoint. To state the properties of adjoint of matrix, we let A and B be any two matrices. Let A and B be matrices. Then, as we have shown earlier, the adjoint of a matrix is equal to the matrix. Similar to the property of transpose, the transpose of a matrix is equal to the matrix. The second property is also similar to one of the properties of matrix transpose. The adjoint of the sum or difference of matrix A and matrix B is equal to the sum or difference of the adjoint of matrix A and the adjoint of matrix B. And the third property of adjoint is not exactly similar to the property of matrix transpose. The adjoint of the scalar product of scalar A and matrix A is equal to the complex conjugate of the scalar A times the adjoint of matrix A. And the fourth property of adjoint, if matrix A is a Hermitian matrix, then the adjoint of A is equal to A. And there is a similar property for transpose. If A is symmetric matrix, the transpose of A is equal to A, if A is symmetric. But this fourth property of adjoint says that if A is Hermitian matrix, then the adjoint of A is A. We take an example to show the fourth property. A Hermitian matrix, as we have taken before, is a square matrix. If we write the entries of the Hermitian matrix H as H sub ij, then the ij entry of the Hermitian matrix this is the property of Hermitian matrix. Aside from being a square matrix, the ij entry of the Hermitian matrix is equal to the complex conjugate of the ji entry. The complex conjugate of the ji entry of the Hermitian matrix is equal to the ij entry of the Hermitian matrix, or the ij entry of the Hermitian matrix is equal to the complex conjugate of the ji entry of the Hermitian matrix, and this must be true for all values of I and j that are not equal. This means that this condition is not true or is not satisfied for I equals j, because for I equals j you will have the diagonal entries of the square matrix or the Hermitian matrix, which is a square matrix. And this is a Hermitian matrix. This entry in the first row and second column is equal to the complex conjugate of the entry in the second row and first column. Because negative 3 is a real number, its complex conjugate is equal to itself. And the complex conjugate of minus 3 is minus 3, which is equal to the entry in the first row and second column of this square matrix H. So this, and there are no values of I and j that are not equal in this matrix, because for this entry, I equals j, one row, first row and first column. And for this entry, I is also equal to j, where I is 2 and j is 2. So we only need to check those entries in the given square matrix, ij, for I not equal to j. And we have seen that this is the complex conjugate of minus 3. And minus 3 is also the conjugate of this entry. So this is a Hermitian matrix. It is a square matrix and it satisfies this property. Now we find the adjoint of this matrix, Hermitian matrix H. And the first step is to get the transpose of the given matrix. The transpose is obtained by writing the rows of the given matrix as columns of the transpose. So this entry 7 minus 3 we write as the entries in the first column. And the entries in the second row we write as the entries in the second column. And this is the transpose of H. And we get the complex conjugates of the entries of the transpose of H for the entries of the adjoint of H, denoted by H star. And because all the entries of the transpose of H are all real numbers, their their complex conjugates are equal to themselves. The complex conjugate of 7 is 7. Complex conjugate of -3 is -3. Complex conjugate of -3 is -3. And complex conjugate of 2 is 2. But this matrix 7 minus 3 and negative 3, 2 is the given Hermitian matrix H. 7, negative 3, negative 3, 2. Therefore, we have shown that if the given matrix is a Hermitian matrix, the adjoint of the Hermitian matrix is equal to the Hermitian matrix H. We now write more properties of transpose and adjoint, and we define skew matrix and skew-symmetric matrix. One of the other properties of matrix transpose states that a matrix A is symmetric if and only if transpose of A is symmetric. Another property states that a matrix A is Hermitian if and only if the adjoint of A is Hermitian. That's a property of adjoint matrix. And another property, if a matrix A is symmetric, then the square of A, or A square, or A to the power 2, which is equal to A times A, is symmetric. In general, if A is a symmetric matrix, the expression A to the power n, or the product of A with itself, or the product of A multiplied by itself n times, is also symmetric. We write these properties in symbols. First property states that A is symmetric, matrix A is symmetric if and only if A transpose is symmetric. And this property can actually be split into two statements. A is symmetric, then its transpose is symmetric. And if the transpose of A is symmetric, then A is symmetric. The second property states that A is a Hermitian matrix if and only if the adjoint of A is Hermitian. As in number 1, the second property can be split into two statements. If A is a Hermitian matrix, then the adjoint of A is Hermitian. And if the adjoint of a matrix is Hermitian, then the matrix A is Hermitian. And number 3, if A is symmetric, then the square of A, which is equal to the product of A with itself, is symmetric. And the more general statement is, if A is symmetric, then A to the power n for all values of n is symmetric. We now define a skew-symmetric matrix. We read the definition. Let A be any matrix, then A is called skew-symmetric if the transpose of A is equal to the negative of A. This is the condition that must be satisfied by matrix A for matrix A to be a skewed symmetric. That is, the transpose of A is equal to its negative. We take an example. Check if this given matrix A is a skew-symmetric matrix. You can see that A has 3 rows and 3 columns. Therefore, A is a square matrix. And we get the transpose of A. The transpose of A is obtained by writing the rows as columns. So the first row of A, 0, 2, 5 becomes the first column of A transpose. And the second row of A we write as the second column of A transpose, 1, 0, 3. And the last row of matrix A we write as the last column of A transpose. Now we get the negative of A, and we will check if the negative of A is equal to A transpose. And the negative of A is equal to the transpose of A if the transpose of A and the negative of A have the same size and their corresponding entries are equal. And to get the negative of A, we apply the definition of scalar multiplication of a scalar and a matrix. The matrix A is multiplied by the scalar negative 1, which is obtained by multiplying each entry of matrix A by the scalar negative 1. And these are the entries of matrix A. We multiply each entry of matrix A by negative 1. And we get 0, negative 2, negative 5. 1, 0, 3 multiplied by negative, negative 1, 0, negative 3. And negative 6, 7, 0 multiplied by negative, we get 6, negative 7, 0. And you can see that the transpose of A is not equal to the negative of A. They have the same entry in the first row and first column, the same entry in the second row and second column, but the other entries are not equal. Therefore, A transpose is not equal to negative of A, and we conclude that matrix A is not Hermitian. We take an example where a matrix is a Hermitian matrix, and we state the properties of skew-symmetric matrix. Consider the following matrix B. B is a 3 by 3 matrix with entries in the first row 0, 1, 2, in the second row negative 1, 0, negative 3, in the last row negative 2, 3, 0. And we will check if matrix B is a skew-symmetric matrix. If B is a skew-symmetric matrix, then the transpose of B must be equal to the negative of B. We start by getting the transpose of matrix B denoted by B to the power T. And to get the transpose of B, we write each row of matrix B as columns of the transpose of B. The first row 0, 1, 2 we write as the first column of B transpose 0, 1, 2. And the second row of matrix B, negative 1, 0, negative 3 we write as the second column of B transpose. And the last row of matrix B, negative 2, 3, 0, we write as the last column of B transpose. Now we get the negative of matrix B by multiplying each entry of matrix B by negative 1. 0, 1, 2 multiplied by negative 1, we get 0, negative 1, negative 2. And the second row of matrix B, negative 1, 0, 3, we multiply by negative 1, we get positive 1, 0, positive 3. And the last row of matrix B, we multiply by negative 1, we get positive 2, negative 3, 0. And you can see that the transpose of B is equal to the negative of B. Therefore, we conclude that the given matrix B is skew-symmetric. Now, we can see that we have shown that B is a skew-symmetric, but if you notice, matrix B is a square matrix, and that's one of the properties of a skew-symmetric matrix. A skew-symmetric matrix is a square matrix, and in addition to that, the entries in the diagonal are 0. And we state that property as a theorem. We read the property stated as a theorem. If A is element of the set of matrices with sizes m by n, m rows and n columns, and the entries of the matrices elements of this set are real numbers, and A is a skew-symmetric matrix, then A is a square matrix, and the entries A sub I, the entry in the ith row and ith column, this is the diagonal entry, or these are the diagonal entries for the row number equal to the column number. The diagonal entries are 0 for I equals 1 to n. We start with A. A is an m by n matrix. Because we know that matrix A is an m by n matrix because it is an element of the set of matrices with sizes m by n and with entries that are real numbers. Then from the definition of the transpose of A, we know that the size of the transpose of A is n by m matrix. The second given in the theorem is that matrix A is a skew-symmetric matrix. And by definition of skew-symmetric matrix, if A is a skew-symmetric matrix, then the transpose of A is equal to the negative of A. And the negative of A, again from the given, since A is skew-symmetric, the transpose of A is equal to the negative of A. And the negative of A is obtained by multiplying the entries of matrix A by the scalar negative 1. And these two matrices, the transpose of A and the negative of A, will be equal under the following conditions. The first condition is that they have the same size. Now the size of matrix A is m by n. So the size of minus A is also m by n, because we only multiply the entries of matrix A by the scalar negative 1. Therefore, the size of negative A, or the negative of matrix A, is m by n. And the size of the transpose of matrix A is n by n. If these two matrices, A transpose and negative of A, are equal, they must have the same number of rows and the same number of columns. And the number of rows of A transpose is n. If A transpose is equal to the negative of A, then the number of rows of A transpose should be equal to the number of rows of negative A, which is equal to m. And the number of columns of A transpose, which is m, should be equal to the number of columns of negative of A. And the number of columns of negative of A is n. Thus, m is equal to n. Now, if n is equal to m, or m is equal to n, if m is equal to n, then matrix A is an n by n matrix. If n is equal to m, then A is an m by m matrix. Again, A is a square matrix. Therefore, we conclude that if A is an m by n matrix and A is Skew-symmetric matrix, we conclude that A must be a square matrix. And we denote the diagonal entries of this A transpose and negative of A have the same number of rows and the same number of columns. So if we denote the entry of A transpose by A sub ij, by the second property of the equality of matrices, the corresponding entries of the two matrices must be equal. So we write also, if A transpose is equal to negative of A, the ij entry of A transpose should be equal to the ij entry of the negative of A, which we denote by negative A sub ij. But we have shown that A is a square matrix, so matrix A has the same number of rows and the same number of columns, or the number of rows of A is equal to the number of columns of B. Therefore, the value of I and j goes from 1 to n, or 1 to m, because n is equal to m. And we simplify this by simply writing A sub ii equals negative A sub ii. Now, the entries of matrix A are real numbers. A is an element of the set of matrices with sizes m by n and whose entries are real numbers. So this number A sub ii is a real number, and negative a sub ii is a real number. They are numerically the same but with opposite sign. This is a positive real number, this is a negative real number. And this can only happen if the real number is 0. Because if the real number is 1, negative 1 is not equal to 1. If the real number is negative 6, take its negative, negative 6 is not equal to negative of negative 6. Or negative 6 is not equal to positive 6. And this can only happen if the real number is 0. Thus, we have shown that the diagonal entries of a matrix A, that is a skew-symmetric matrix, are 0. In this theorem, again, we have shown that if A is a skew-symmetric matrix, then it is a square matrix, and as in this example, B, and the diagonal entries are 0. And we state another property of the skew-symmetric matrix is that if a matrix A is a square matrix, then A minus transpose of A is skew-symmetric, while A plus the transpose of A is symmetric. Again, this property of a matrix, a square matrix, if a square matrix A has the same number of rows and the same number of columns, or simply if a matrix A is a square matrix, then A minus the transpose of A is skew-symmetric, and A plus the transpose of A is symmetric. And we will state this property as a theorem in the next lesson, and we will prove this property. And also we will define in the next lesson invertible matrix. Thank you for joining me in my class today in linear algebra.